Today's lesson is on the calculus of variations.
Hey, welcome to Easy Lecture. I'm your host, Professor Ashley Carter from Amherst College's Physics Department. We've got a great series of lectures planned for you on physics and math concepts. Let's get started. We all know that the curve with the shortest distance between 2 points is a straight line. Can you prove it? Chances are good that you're probably drawing a blank. Let's try another problem that's similar. This problem is generally referred to as the brachistochrone problem. Let's say we want to know which ball on this demonstration will finish at the bottom first. To figure out the answer, we need to know which path takes the least amount of time to traverse. If you think about it for a second, you may be stumped. On the one hand, we want the path with the shortest amount of distance, which is the straight line. On the other hand, we want the ball to have the largest amount of velocity for as long as possible. So maybe these paths that are steeper at the beginning would be better. Is there some way to figure out the answer before we race the balls? Finally, this last example is one of my favorites. Let's say that the problem here is to predict what the soap film will look like when I lift these two wands out of the soap tray. In this case, the two different wands are two different sized circles. Some of you may think you know what the shape will be when I lift the wands out. Perhaps you're drawing from your experience with bubbles as young children, or perhaps you know that the soap film will adopt the shape with the least amount of surface area in order to minimize surface tension. This is why a bubble is round, no matter what the shape of the wand is. Using this information, can you mathematically find what the surface with the minimum surface area will look like between our two wands?
In this lesson, we are going to introduce the calculus of variations. By the end, you should know how to set up a variational problem by writing down the appropriate functional, and you should be able to solve a variational problem using the Euler-Lagrange equation. Our text of reference will be the Mathematical Methods in the Physical Sciences by Mary Boas. We're going to be looking at Chapter 9, Sections 1 through 4. Our first goal is to set up a variational problem by writing a functional. To set up a variational problem, we'll begin by drawing 2 points on a page. Note that these must be the endpoints for the curve. Next, we'll want some mathematical map that relates each curve between these 2 points to the distance of the curve. Specifically, we want a function that takes one of the curves as an input and outputs the distance. A function that does this is called a functional. A functional is really a function of a function. It could represent distances for a series of curves, areas for a series of surfaces, or the total transit time for a series of paths. The key is that the functional takes a function as the input and spits out a scalar, in this case, the distance. So now we need to write down this functional. For our problem of finding the curve with the shortest distance, we already know what our functional will be. After all, if we want to find the distance s along a curve, we just need to take the line integral. So to find s, we're just going to integrate from point 1 to point 2 ds. The trick to setting up this line integral is that we need to write it using the correct variables. For example, say we want to find a curve y of x that is the shortest distance between x1, y1 and x2, y2. Well, in this case, we're going to want to rewrite ds, which is the infinitesimal distance along the curve. And we're going to want to rewrite that in terms of dx and dy. We can do this by using the Pythagorean theorem. Here I've just written ds as the square root of dx squared plus dy squared. And since we want to integrate along x from x1 to x2, we're going to need to rewrite the integral again and factor out the dx. If we factor out the dx, we get this expression, and now we're going to integrate from x1 to x2. And there it is. We have our functional. This functional takes a function, the derivative of y, and outputs a scalar, the distance along the curve y of x. It turns out that for a variational problem, all of our functionals will be definite integrals. The general form of these integrals will be integral of f dx, where f is a function of x, y, and the derivative of y with respect to x. Here I've written x as the independent variable and y as the dependent variable. You should of course be able to change variables at will. I is just the scalar that it's output by the definite integral. When you go to set up a functional problem, your goal will first be to set up this integral. Let's go ahead and see if you can set up some definite integrals on your own. First, let's set up the definite integral to find the distance along the curve x of y between 2 points in the xy plane. You should have set up the following integral, integrating from y1 to y2, the square root of 1 plus dx dy squared times dy. Let's try another one, but let's use 2D polar coordinates. In this problem, I want you to set up the definite integral to find the distance along the curve r of phi between 2 points in the xy plane. Here we have to remember that when we switch variables, the ds term will have an r d phi term and a dr term. Don't forget this r in the r d phi. If we factor out the d phi, we'll get this integral here. I hope you were able to find it. Let's do one more. This time, let's set up the definite integral to find the distance along the curve z of phi between 2 points on a cylinder of radius r. The long axis of the cylinder points along the z-axis. To solve this problem, we just have to find the ds term in 3D cylindrical polar coordinates. ds on the cylinder will be given by the square root of big R d phi squared plus dz squared. If we factor out the d phi, we get this expression. Again, we want our integral to go from phi 1 to phi 2.
Now that you've set up several definite integrals for finding the distance between 2 points, let's turn our attention to the brachistochrone problem. In this problem, we want to find the path between points x1, y1, and x2, y2 that gives the shortest transit time for the ball. Let's set up this definite integral to find the path with the shortest transit time.
For this brachistochrone problem, we want to set up the definite integral to find the transit time for a ball on a brachistochrone along the curve x of y. To set this up, we need to use the fact that the velocity is a function of height, you should remember what that is from introductory physics, and that the velocity is also equal to ds dt. Go ahead and find the definite integral for the transit time. You should have started this problem by writing down an integral from point 1 to point 2 of dt. Then you should have inserted ds over v for dt. Now all you have to do is substitute expressions for ds and v with variables x, y, the derivative of y, dx or dy in them. ds is of course just the square root of dx squared plus dy squared. V is just the square root of 2 times the gravitational constant g times the height y. You should remember this expression from introductory physics. If you've forgotten this expression, you can rederive it by setting the kinetic energy equal to the potential energy. Finally, the last step is to factor out the dy to change the definite integrands from y1 to y2. And voila! We now have found the definite integral that gives the transit time for the ball in the brachistochrone problem. We've just got one more definite integral to set up, and that is for our soap film problem.
In the soap film problem, we want to find the surface area for the surface between these two circular wands. More specifically, we have 2 points. One point is on the first wand, and one point is on the second wand. We're going to draw a curve between the 2 points, and then we're going to revolve the curve around the x-axis to create a surface of revolution. We want to find the curve such that the surface area of our surface of revolution will be a minimum. Let's go ahead and define this mathematically.
For the soap film problem, we want to define the surface area of our surface of revolution. And so we of course are going to need to define a definite integral. In this case, the surface area is just going to be the integral from point 1 to point 2 of dA. And dA, of course, is just equal to the circumference at each point multiplied by the infinitesimal length ds along the curve. Your job is to find an expression for ds and set up this definite integral to find the curve x of y. To solve this problem, you should have plugged in the definition for ds, which is just square root of dx squared plus dy squared. Then you can go ahead, factor out the dy, and set the integrands from y1 to y2. This will give you the correct definite integral. If you were able to set up this definite integral, then good job! You are now ready to go on to the next section. If not, you can get some extra practice by completing problem 6.6 in Taylor's Classical Mechanics.
In the last section, we talked a lot about setting up a functional or definite integral for our variational problem. But once we have that functional, we still need to find the minimum of the functional to get the curve at the minimum distance. So how do we do this? Let's first review how to find the minimum of a function, and then we'll talk about how to find the minimum of a functional.
In the next section, we'll solve a variational problem using the Euler-Lagrange equation. Say we want to find the minimum of a function f of x. How do we do this? You should have learned in calculus that you need to set the derivative of f to 0. If f prime of a equals 0 and f prime of b equals 0, then both a and b are called stationary points. These points could be minima, maxima, or inflection points. To figure out if these stationary points are minima, we need to take the second derivative. If the second derivative at the point is greater than 0, then the stationary point is a minimum. Perhaps we can do something similar to find the minimum of our functional. Here I have written the general definite integral for the functional as the integral from x1 to x2 of f dx. Taking the derivative of this definite integral seems like a large task. To do this, we're going to need to use the calculus of variations. The calculus of variations is a field of mathematics that seeks to find the stationary path of a functional. In other words, the calculus of variations seeks to find paths that give stationary values of this definite integral. Let's use the calculus of variations and derive the Euler-Lagrange equation, which will then give us the stationary path to this integral. To start, let's assume that we already know what the stationary solution is. Assume that it is little y of x. Now let's try to define an arbitrary curve, big Y of x, in terms of our little y of x. Both big Y of x and little y of x are going to pass between the two endpoints, and both are single-valued and contain a continuous second-order derivative. We can then write big Y of x in terms of little y of x and another function, eta of x, multiplied by a constant epsilon. The function eta of x is also single-valued and has a continuous second-order derivative. In addition, its endpoints must be 0 so that big Y and little y of x end at the same point. Now let's reformulate the problem so that we find the stationary values of the definite integral with big Y instead of little y. This integral isn't going to be a scalar anymore. It's going to be a function of epsilon. You can see here that once we integrate over x, we will still have all of the epsilons left in our solution for the definite integral. Now it may not look like it, but this rewrite gives us a big advantage. This is because we already know what the stationary path of the integral is. It's little y of x. So we know that the stationary path occurs when epsilon is 0. Thus, the derivative of I with respect to epsilon will be 0 when epsilon is 0. Let's go ahead and find the derivative of I with respect to epsilon and set it equal to 0 when epsilon is 0. Taking the derivative inside the integral requires the use of the chain rule. Of course, we can simplify this equation because when epsilon is 0, big Y is equal to little y. and the derivative of big Y with respect to epsilon is eta. The derivative of big Y prime with respect to epsilon is eta prime. Knowing this, we can substitute in these values into our equation. We can further simplify things by noting that the second term in the integral can actually be integrated by parts. The result is the following equation. Now you should check this result later while following the derivation in your textbook, because we won't go through that check here. It turns out that the first term in this equation is actually 0. That's because the endpoints of the function of eta are 0, leaving only the second term. Plugging this back into our original equation yields an integral with two terms. Since eta must be arbitrary and can't always be 0, we find that this inner term must be equal to 0. This equation is called the Euler-Lagrange equation, and it gives us a differential equation that we can solve to find the stationary path y of x. It turns out that any variational problem can be solved using this equation because it is completely general. So if we have a variational problem, all we need to do is first find the integral. Second, find the differential equation using the Euler-Lagrange equation. And third, solve the Euler-Lagrange equation to find the stationary path. Now that we've defined the Euler-Lagrange equation, let's use it. In this problem, I want you to find f and its partial derivatives and plug them into the Euler-Lagrange equation. The function f should just be this term inside of the integral. To save space, let's write dy dx as y prime. In this function, there are not any terms with y, only terms with y prime. So the partial of f with respect to y is 0. The partial of f with respect to y prime is just going to be y prime over the square root of 1 plus y prime squared. Remember, when you take a partial derivative, you're going to want to treat all other variables, except for the variable that you're taking the partial with respect to, as constants. Now that we have these partial derivatives, we can substitute them back into the Euler-Lagrange equation, and we find the following differential equation. Now what I'd like you to do in the next problem is just to solve the Euler-Lagrange equation to find the path that makes the integral stationary. To solve this problem, we first note that there is no x in this expression. That means that we can take this expression and set it equal to a constant. If we rearrange, we find that y prime is constant, and therefore y is equal to ax plus b, where both a and b are constants. This is just the equation for a line. Thus, the curve with the shortest distance between 2 points is a straight line. Let's go ahead and solve another problem. This time, let's solve the brachistochrone problem. For the following integral, find big F and its partial derivatives and plug them into the Euler-Lagrange equation. First, we'll find F. Again, F is just the expression inside the integral. Note that the independent variable is y and not x. You'll have to make sure that you're comfortable with switching between y and x very easily. Now let's find the partial derivatives of f. The partial derivative with respect to x is 0, and the partial derivative with respect to x prime is this expression. We're going to go ahead and plug these expressions into the Euler-Lagrange equation. We end up with an equation where the negative of d dy of this expression is 0. That means that we can take this expression inside of the parentheses and just set it equal to a constant. It turns out the path with the quickest transit time is actually a cycloid, and this is the differential equation for a cycloid. This derivation is done for you in Boas, Chapter 9, Section 4.
Now that we know that a cycloid is the quickest path for the ball, we can make our prediction. Of course, some of you are probably wondering which path is the cycloid. It turns out that this path is the cycloid. You can see that it drops steeply, and then it starts to move across, so it doesn't increase the distance too much. If we now pull this tab and race these balls, we should see which ball is the winner. It looks like the ball in the cycloid won, just as we predicted. Great work! Now we just have one more problem to solve, and that's what our soap film surface will look like when we put these two wands out of the bubble solution.
Our last problem is to ask which surface will have the minimum surface area between our two circular bubble wands. We've already found that the definite integral for the surface area is just going to be 2 pi times the integral from y1 to y2 of y times the square root of 1 plus x prime squared dy. Go ahead and find f, its partial derivatives, for this integral and plug them into the Euler-Lagrange equation. You should have found that the function big F is just the expression inside the integral. Again, watch your notation. This big F has the independent variable of y. The partial derivative of big F with respect to x is 0, and the partial derivative of big F with respect to x prime is just this expression. If you plug in these partial derivatives into the Euler-Lagrange equation, you end up with this expression. Again, setting the expression in the parentheses to a constant will give you the differential equation. If you solve this differential equation, you'll get the hyperbolic function of a cosine. Here, a and b are just constants. And while this equation probably doesn't look familiar, the shape it makes is called a catenary.
A catenary is a curve a rope makes if it is held between 2 points and allowed to fall due to gravity. Our soap film should actually be a surface of revolution for a catenary, which is called a catenoid. Let's go ahead and make our soap film between these two circular bubble wands. It should be a catenoid. Let's see if we can see it. Yes, it is a catenoid. The first time I did this experiment, I was pretty amazed. I remember thinking the curve should just be a straight line between the two wands, but that's not correct. The curve is actually a catenary. I bet when you see a power line hanging between two towers, you won't look at it the same way again. Instead, you'll think, ah, a catenary. That's all the problems for today. If you want more practice, you can try the problems in Chapter 9, Section 3 of BOAS.
Conclusion. Today we've talked about the calculus of variations. We've talked about how to set up a variational problem by writing down the appropriate functional, in this case, the definite integral. And we've also talked about solving a variational problem using the Euler-Lagrange equation.
The techniques that we've learned today will ultimately be helpful in solving variational problems. That is, problems that require you to find the stationary solution of an integral. And while it may seem like there are not very many variational problems, it turns out that there is an incredibly important variational problem in classical mechanics. In fact, we will see that we can totally reformulate Newton's laws in terms of the Euler-Lagrange equation. We will call this Lagrangian mechanics, and it will be one of the main topics of the class. So knowing how to set up the definite integral and how to solve it using the Euler-Lagrange equation will be immensely useful. That's it.